First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great. First you separate, and then you integrate. Just follow these steps, and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Greetings, calculus students, and welcome to lesson number 3. Okay, today's lesson is all about finding limits analytically. That means basically using some algebra to figure the limit out. On today's agenda, we'll first begin by reviewing what we've covered previously, and then we'll get to finding limits analytically. So I'm going to go ahead and bring a graph up, and with that graph, I'm going to review what we covered yesterday, which was finding limits graphically. So I'm going to look at the limit at a couple of different places on this graph to make sure we still have a firm understanding of that particular concept. So there's a nice little graph, and so there are three x values I want to find a limit at for this particular graph. I think 2 of them probably kind of stick out to you. So first I want to find a limit, and this is the graph of f of x. Let's call this the graph of f of x. And the first thing I want to do is find a limit of f of x as x goes to -2. I want to find a limit of f of x as x goes to -2. I want you to look at this as well. Pause the video if you need a little time. Then I'm going to go ahead and go over the solution. So again, as I look at x goes to -2, I'm looking from the left and from the right. I need to see agreement. I do see that agreement, and I see the y values are going to 1 as it approaches -2 from the left and the right. So the answer is 1. Again, the value at the point, which in this case is 3, has no bearing on the value of the limit. Next, I would like to look at the limit as x goes to -1. So I want to look at the limit as x goes to -1 right here. Again, pause the video if you need a couple seconds to figure this out, and then I'm going to go over the solution. So looking at -1, and so mainly in these problems, when I'm finding a limit at a particular point, there's something interesting going on at the point. Generally, there's some type of discontinuity, but sometimes we find limits at points where there's really nothing going on. Generally, it's continuous at that point, and that's what's happening here as x equals -1. At -1, it's continuous, it's smooth, there's no open circle, no vertical asymptote or anything like that. So the limit, you can see, well, we can look at it from the left and the right. From the left, we're going to 2 as x approaches -1. From the right, we're going to 2 as x approaches -1. So the limit of f of x as x goes to -1 is 2. So sometimes we do see those nice problems like that, and they're nice when the value that we're finding the limit at, the function is continuous at that point. So the last one I want to look at is the limit as x goes to +1. And that's this guy here. And so again, if I look at the left and the right, from the left, it's going to 2. From the right, it's going to 1. So it's going to 2 different numbers from the left and the right. So we say D and E, the limit does not exist. All right, so now let's go ahead and look at limits analytically. What I'm going to do is all those limits we found with the calculator and tables on lesson 1, I'm going to work those limits out and find those limits analytically. So I'm going to do all the limits we did on lesson 1, and I'm going to do an additional one that wasn't done on lesson 1 at the very end, but I'm going to do all those limits analytically. So let's go ahead and have a look. So I just want to stress one thing before we start finding limits analytically, because part of the process is going to seem like a big contradiction to what we've been stressing before. So, and here's the deal. So when we've been finding limits numerically and graphically, we've been stressing the point that when finding the limit, I'm not concerned necessarily with the value of the function at the point the limit is going to, but I'm concerned as x approaches that particular point from the left and from the right. And all that still is a universal truth. However, the type of functions that we're going to be finding the limits of analytically today we're able to plug the value in for x. In fact, the first thing we do for these type of problems, for finding the limit of f of x as x goes to c, the first thing I actually try to do is plug the value into the function. If I get an answer when I plug it in, that answer is actually the limit. So for these problems, and these are special type of functions, and we'll get into the type of functions they are tomorrow, the type of classification they have, which allows us to do this. But these are special type of functions where if f of c exists, it's going to equal the limit. So for the type of problems we're going to do today, and again, tomorrow we'll get in more detail about what makes these, which allows us to do this for these type of functions, and also what type of functions we would not be allowed to do this. But for the type of functions we're going to do today, we're allowed just to try to plug the number in for x that the limit is going to. We call that method direct substitution. If that yields an answer, so sometimes it doesn't yield an answer, meaning sometimes we plug the number in and the function is undefined at the point. So that's what I mean by if it yields an answer. If it yields an answer, if it's defined, if f of c is defined for these type of problems, and again, tomorrow, you know what I mean by these type of problems, but if f of c is defined for these type of problems, then that is also equal to the limit. Now, if f of c is not defined for these type of problems, there are going to be two scenarios of the type of problems we see today that could happen. One is we can plug in the value into the function and we can get 0 over 0, the indeterminate form. Now, if we get 0 over 0, that's actually good news. That's pretty good news. That is an indication of hope to find the limit. So if we get 0 over 0, there is hope that we can find a limit, and I'll explain as we do the examples. The second thing that can happen is we can get a constant over 0 or a non-zero number over 0. So not 0 over 0, some non-zero number over 0. If that happens, we're done. So there's no way we're going to be able to find a limit. It's going to be D and E. So there's going to be 3 scenarios on these problems. On all these problems, we're going to try to plug the value that the limit is going to into the function. So on all these problems, the first thing we're going to do is try to find f of c. If f of c exists, that's our answer. If f of c doesn't exist and it's in the form of 0 over 0, there's hope we can still find the answer, and I'll explain how we can get the answer from there. And lastly, if f of c is undefined under the form of k over 0, where k is a non-zero constant, it's going to be D and E. So without further ado, let's kind of look at some examples to bring what I'm saying to a little bit more clarity. Okay, so for our first problem, we have the limit as x goes to 5 of x squared plus x minus 30 over x minus 5. Now, again, the first thing we want to do is we want to try to plug 5 in for x. If we get a number, that's the answer. If it's undefined, we'll look at what it comes to, whether it's 0 over 0 or k over 0. So we have 5 squared plus 5 minus 30, which is 25 plus 5 minus 30, which of course is 30 minus 30, or 0. So our numerator would get 0. Our denominator would get 0 as well, because our denominator would simply be 5 minus 5. So when plugging in the number, it's undefined, but it's 0 over 0. So again, 0 over 0 is an indication of hope that we can still perhaps find the limit, that the limit may exist. If I had got a non-zero constant over 0, k over 0, there would have been no hope. So this 0 over 0 is what we call the indeterminate form. And how we try to find the limit when we get this 0 over 0 indeterminate form for right now will be by factoring and simplifying. So we're going to try to factor and simplify in order to plug the 5 back in and get the answer. A little bit later, we'll learn something called L'Hopital's rule. which will allow us to do it with derivatives. But since we don't know derivatives yet, we're going to utilize something we do know, which is factoring. So let me just write the function again, which is x squared plus x minus 30 over x minus 5. And I can factor my numerator as x plus 6 times x minus 5, of course, over x minus 5. The x minus 5s cancel, leaving me with x plus 6. So that simplified to x plus 6. Well, what that means is that I can find the limit of the first function as x goes to 5. So I can find the limit as x goes to 5 of the original function. So I'll go ahead and write it. And that will equal the limit as x goes to 5 of x plus 6. And of course, remember, for these type of functions, and again, these will be explained later, if I want to find a limit, I simply plug the number in. So to find a limit as x goes to 5 of x plus 6, all I do is plug in 5 for x. So that's 5 plus 6, or 11. Now, some may wonder how finding the limit of x plus 6 could be equal to the limit of x squared plus x minus 30 over x minus 5. And I submit to you that these two functions are actually equivalent in all values except for 1. So I'm going to call the first original function f of x. So f of x is x squared plus x minus 30 over x minus 5. I'm going to call the second function g of x. So g of x is x plus 6. And I'm going to use just some sample values. So for instance, I'll plug a few numbers in to f of x. And I'm going to show you those are the same values if I plug the same number into g of x. And there's only one value when they don't agree. So let's say I find f of 10. If I plug in 10 into f of x, I'm going to get 16. Let's say I find f of negative 3. If I plug in negative 3 into f, I'm going to get 3. But now let's say I find f of 5. If I plug 5 into f of x, it's undefined because it makes my denominator 0. And that is the only value for x where f of x has a different value than g of x. For instance, g of 10 is 16, that's easy to see. G of negative 3 is 3, that's easy to see. And g of 5, of course, is 11. So we have a rule, and I'll explain in a little detail why the rule works. And the rule is, if you have two functions that agree on every point but c, so I have two functions that agree on every point but c, and the limit as x goes to c of the one of the functions is defined, you can find that limit, then that means the limit as x goes to c of the other function must be the exact same thing. And the best way to understand this is from a graph. It's very easy to see when you look at the graph. So let me kind of give you the graph of both these functions to make this a little more clear. So let me start with the graph of g, since that's the easiest one to graph. It has an x-intercept of negative 6, y-intercept of 6, and we'll pay attention to the 0.5 because that's where the limit is going to. And it's not really up to scale because my 5 is farther than my negative 6, but you understand my struggle. So let's draw this in blue. And I kind of missed the y-intercept a little bit, but you know my intentions. And that's the graph of x plus 6. And we kind of know what that graph looks like. Now the graph of f of x, well, let's show that at 5, the function is 11. Now the graph of the other function, it may not be so clear. So let's look at the graph of f of x. Now remember, f of x is the same as g of x, except where x is 5. So it also has a y-intercept of 6 and an x-intercept of -6. And we'll also look at when x is 5. So again, it's that same line. The only thing is when I get to 5, I have an open circle because the graph is undefined when x equals 5. That is the only difference. That is the only difference between a graph of f of x and the graph of g of x. And if you remember what we said about finding limits from graphs, you can easily see why these limits are the same and how limits will be the same when you're taking a limit as x goes to c and both functions agree on every value except for c. I think that's clear to see why those limits would be the same from a graphical standpoint. Okay, the next example is the limit as x goes to -2 of 12 over x plus 2. Okay, so again, for these type of problems, first thing we'll try to do is plug in the value for x to see if we get a number. So I'm going to plug in -2 for x, and that will give me 12 over -2 plus 2. So I get 12 over 0. Now 12 over 0 is a problem. So I plugged the number in, it was undefined, just like the previous problem was undefined. But this is undefined in a different manner. So remember, when we get 0 over 0 for our undefined, we have hope. But when we get k over 0, where k is a non-zero constant, we have no chance. Meaning it's going to be D and E. We have no chance of finding the limit. And the reason being, just in quick, why 0 over 0 is hope and k over 0 is no chance. The problem with these problems is our denominator being 0. That's what makes them undefined, our denominator being 0. So when you have 0 over 0, meaning the factor making your denominator 0 is also in the numerator. So meaning many times you can cancel them out. But when you have k over 0, that means the factor making your denominator 0 is only in your denominator and it can't be factored out. So that's why it stays D and E and there's no hope. Next example, we have the limit as x goes to 7 of x squared minus 9x plus 20 all over x minus 6. So again, we're going to try to plug in 7 for x, see what happens. So we get 7 squared minus 9 times 7. I need a better 7 than that 7. 9 times 7 plus 20. Let's go ahead and evaluate the numerator first. So that's going to be 49 minus 63 plus 20. So 49 minus 63 is negative 14. So negative 14 plus 20, of course, is 6. And our denominator is just 7 minus 6, which is 1. So we get 6 over 1, which is 6. So that's the answer. So again, if we plug in the value and we get a number, if it's defined for these type of problems, that's the value of the limit. It's only when it's undefined, whether it's 0 over 0 or k over 0, where, well, really it's only when it's 0 over 0 when we have to look at factoring. Of course, when it's k over 0, it's D and E automatically. All right, next one is the limit as x goes to 1 of the absolute value of x minus 1 over x minus 1. And now I know the title of this is Finding Limits Analytically, but I'm really going to do this one graphically. So this type of limit, I'm going to graph it, but I'm going to graph it by hand. So the graph of this function is something you should be very familiar with. So this one is really understood better. This one and the next one actually is really understood better from a graphical standpoint. But I'm not typing it in the calculator to graph it. So you have to understand the way this graph behaves to do this problem. So this is a very common function that you'll see. So I'm going to say f of x is the function. Just going to call it f of x. So I can do some operations in easy notation here. So f of x is the given function. And let's say we let a be greater than 1. So a is a number which is greater than 1. So think of any number you want that's greater than 1. Any number you can think of. And I'm going to find f of a. So if you plug in any number greater than 1 into this function, what do you get? You should get 1. So look at it very clearly. Any number greater than 1 in that function should give you 1. And now let's say we let b be less than 1. So b is any number less than 1. So think of any number less than 1, plug it into this function and see what you get. So you can think of any number less than 1. The thing that's going to happen is the value is going to be negative in the denominator, but positive in the numerator because of the absolute value sign. So f of b is going to be negative 1 for whatever number you try. See, when the number was greater than 1, both top and bottom were positive, but here they weren't. And also, of course, we got greater than 1 and less than 1. But how about when we take the function at 1? That, of course, is undefined because it makes our denominator 0. So I'm going to use these three understandings to plot the graph of this particular function. So I need to mark at 1 here and 1 there and negative 1 there. So for numbers which are less than 1, we got negative 1. So all the numbers less than 1 gave us negative 1. So that's going to give us a horizontal line going through negative 1 all the way till we get to 1. Open circle on 1 because at 1 it's undefined. And then for greater than 1, we get positive 1, so we get a line that looks like that. So that's how the graph of that function looks. Again, become accustomed with how that graph looks. Now, if we look at the limit, it's approaching two different numbers from the left and the right of 1. Negative 1 from the left, positive 1 from the right. So we know that limit doesn't exist. That's what we call a jump discontinuity, which of course means that the limit of this particular function does not exist. So that limit this limit is a DNE. We're going to look at our next example. Again, all of these problems were the same problems we did numerically on lesson 1. So the next problem is a piecewise function. It's the last function we did on lesson 1. I'm going to do one more after this, which we didn't do on lesson 1. So the first piece was 5x minus 3 when x is not equal to 2. And the second piece was x squared when x is equal to 2. Sometimes people have a misunderstanding of these piecewise functions. You would think x equals 2 is more important, but actually the most important part of this function is the part when x is not equal to 2. This top piece is the main part of the graph because it represents every x value other than 2. The bottom one only represents when x is 2. That's 1 point. The top one represents an infinite number of points. So the main part of this graph is going to be the graph of 5x minus 3. And so that has a y-intercept of -3, not +3. Let's get rid of that. So this one's going to have a y-intercept of -3. And we need one other point. So say we plug in 1 into this function. So f of 1, that would be 2. So we can also plot a point at 1, 2, and then draw a line. And again, not really very good up to scale because my 2 is higher than my 3, but you kind of understand what I'm going for here. Now, so this is basically 5x minus 3 is the graph of this whole function, except when x is 2. So when x is 2, we'll have an open circle on this because it says x is not equal to 2 for 5x minus 3. And so the graph we have to use at 2 is x squared, and f of 2 is 4. The graph of x squared is a parabola, but we're only plotting 1 point. So we're going to put a closed circle on 4. Now again, it may not look good, but 4 is going to be lower than the open circle because the open circle is supposed to be at 7. So 4 is just a little bit under there. Again, I guess I could have scaled my drawings a little bit better, but I think you understand my mathematical intention here. So the lower circle is at 4, the open circle is at 4. Excuse me, the closed circle is at 4, the open circle is at 7. So you can see there that the limit is 7 as it approaches from the left and from the right. It's going up there to where that open circle is, and that again is at 7. And how do we know it's at 7? Because if you plug in 2 to 5x minus 3, you get 7. Okay, last example. So this last example was not done in lesson 1. I'm using this example to prove a point. So I don't want f of x. I want to find a limit. So let's say we take the limit as x goes to 3. And we'll do it of x squared plus x minus 12 over x squared minus 6x plus 9. All right, so let's do what we normally do. Let's plug the value in for x and see if we get something that's defined or not. So in the numerator, we have 3 squared plus 3 minus 12. That's 9 plus 3 minus 12. That's 12 minus 12, so that's 0. See what happens on the bottom. On the bottom, we'll have 3 squared. So 3 squared minus 6 times 3 plus 9. So that's 9 minus 18 plus 9. So that's 18 minus 18. So that's 0. So we get 0 over 0. So there's hope. So we may be able to find this limit. Again, 0 over 0 doesn't guarantee the limit exists, but there's hope that you can maybe find the limit. So we have hope. So we're going to try to factor this expression and see what happens. So let me just keep the limit here so I can see the function and get rid of this. and let's begin our factoring. So I'm going to factor the numerator as x plus 4 times x minus 3. The denominator is x minus 3 times x minus 3. X minus 3 cancels. It's a 1-for-1 cancellation, not a 1-for-2. So we get x plus 4 over x minus 3. The unfortunate circumstance, however, if I was to plug 3 into this new function now, x plus 4 over x minus 3, I get 7 over 0. So I got that k over 0 issue. So that means this guy is going to end up being a D&E. So the whole point of this problem was to show that even when you get 0 over 0 initially, it still could turn out that the limit doesn't exist. And of course, the main reason you're seeing here how that can happen is if the factor that's causing your denominator to be 0 occurs more times in the denominator than it does in the numerator. So the factor will be left there after you cancel it out. Okay, so that completes lesson number 3. Hope it was enjoyable, and we'll see you next time.
Was a kind of a mathematical outlaw, a kind of a mathematical gangster. He did things which were unlawful and illegitimate.